All right, we are getting into really now the kind of the twist here, or the unique take that Lockbit has on this API hashing. I mean, we've already seen a little bit of it throughout these videos. In particular, not an incredibly advanced technique, but in using a constant XOR with those pre-computed values, it makes it a little bit less straightforward to identify the use of which APIs they're calling. But now we get to see this sort of trampoline that they're creating, and actually why this new heap and this pointer to allocate heap is being passed into this function 405DA0. So we're going to spend the next bit of time here, however long it takes me, hopefully to get you through pretty good understanding of what's happening here and how this is actually kind of clever, kind of neat. It is different than typically what you'll see when using the API hashing. So without further ado, let's get into sub 405DA0. You can see that this is going to be the predominant function called here as we're rounding out our analysis of this runtime linking. Now, just to rebase ourselves a bit, we have 4 arguments. We've identified the last 2. The third argument is going to be the new heap. We discussed in a previous video where that was being allocated just up above here in the logic. We have a pointer to the function RTL allocate heap. You're going to see these two are going to play together, and that this will be the function that is called in order to allocate memory on the new heap. And then we have our first 2 arguments. And if we take a look at the first argument, you'll see that right now this is saying that it's just an unknown sequence of bytes. It then turns into these D words later. This is a good indication that this is the location where those imports are going to be stored. So essentially our new import table. The second argument, you can see this an array of D-word values. And not only do we have these array of D-word values, 4-byte values, but you'll notice that as this chunk of values ends before we have a reference to another, and then this chunk ends, we have the hex value CC, which then is used as an indication that this is the end of that array of hashes. Therefore, all of the APIs have been resolved. You're also going to see as we get into the logic, but I just want to point it out here that this actually is going to indicate the DLL to load, and then these will be the APIs in the DLL, and then of course here we have the end of all the imports. So it's going to do this essentially one library at a time. Okay, so how do we figure all that out? Well, let's drill down into this function 405DA0. First thing I want to do is just make sure that these arguments here are properly typed and have a proper name. So this is going to be actually an int pointer. We can call our A1 here. That'll be our DLL. Let's just call it new imports. Okay, the second, a D-word pointer. Yeah, I mean essentially it's the same thing. I guess we could type it as an int. And this is going to be our pre-computed checksums. Okay. Now we have for A3, this is going to be, let's change the type. We'll say that this is a void pointer. And A3 is going to actually be our new heap. And very similar with this final argument, let's change the type because it's unnecessarily convoluted. Let's just say this is also a void pointer. Well, I guess we could look up. Let's see if I could do that real quick. MSDN RTL allocate heap. There's our function on MSDN, and it's going to down here. The return value is a pointer to the newly allocated block of memory. Yeah, so I'd say void pointer because we don't really know the type for what this memory is going to be used as. It's just a new chunk of memory. So we'll call that a void pointer. That simplifies that just a tad. And then let's rename A4. We'll just call that pointer to RTL allocate heap. Okay, so I think that will make the pseudocode here, the decompile view, just a little bit easier. Let's just kind of work through this kind of top to bottom, and you'll see as we get through here, we'll get a little bit repetitive as we get a little bit further down here. So it's really just a little bit of work here up at the very beginning. As I've done with the previous videos, I'm going to use a combination of the disassembly and the pseudocode here. This first, we have the precomputed checksums plus 1, and that's being loaded into this var4. var4 is going to be used a little bit later on. So what we can see here then is that argument, that pointer to those precomputed values being moved into ESI. That load SD then will take that first 4-byte value, and that's going to move that into EAX. That will also then increment our pointer in ESI. Okay, now we have in EAX the first checksum value. That's going to be XORed with this constant, and then it's going to be pushed as an argument onto the stack for a call to sub 405C24. Now, we can navigate into this function, and you can see that some of our previous work is paying off a little bit here. We have this direct API resolution, which we know then will resolve an API. You can actually see, I think in the pseudocode a little bit better, similar pattern here of some global variables. If they're not identified or if they're not defined with a value, this is going to initialize some of those. So this is going to be some libraries, no doubt, that are going to be utilized in order to load libraries, most likely. We could, kind of two options here. To be realistic about how I analyze, I don't always take the time then to go through all of this logic again, right? I mean, we're already, just from this video sequence alone, which I've fine-tuned for the recordings, you don't get all of the time it actually spent me to figure all this out. You just get the polished version. I start to say, okay, I don't really have the time or the interest to go through all of this. The easy button, in a sense, would be then just to look at, well, what value is being returned here in EAX. We know it's the first 4 bytes, right? So we have the first 4 bytes from this array of hashes, so we can see that. And you can actually kind of see that the checksum values look a little bit different. But we can also then just identify, and let's go back to where this is called, what's returned in EAX, right? And so that's likely what I would do here. Let's copy that address, 5db5. We'll go to debugger. I already have it running. I'm just going to confirm the address, E10000. So that's the image base. So E1, and we'll paste that in. Okay, so now we have our breakpoint set. I might have previous breakpoints. Okay, I think I'm good here. So let's just go ahead and we'll begin execution. And there we go. We hit our break after that call in EAX, and you can see that in the EAX register we have the image base for NTDLL. Right. Well, this is the only breakpoint I have. And so, okay, that returned NTDLL in that instance. Well, let's just step through again. You can see now it's kernel 32. We can step again. Now it's ADV API 32. So that really does, I think, give us a pretty, I'm fairly confident at this point that what this is doing is it is, resolving the DLL base based off of those, whatever value is provided here as the first checksum in that array of precomputed values, right? Same XOR, same hard-coded constant before it's pushed on and resolved. So, now we don't have to necessarily go through all of this logic. We did a few test runs. We got, I think, a pretty good sample here in order to be fairly confident that that's what's happening. That's being stored in this result variable. So we could say that this is now our DLL base. Again, it's always, I think, a good practice to rename and retype as you go, because it can oftentimes help later on as you're trying to figure out what's actually happening in this logic. So if that returned the pointer to the base of the DLL, then great. We're going to continue on. Next thing that's going to happen is the new import table is going to be moved into EDI and then adding to EDI 4. So essentially that's now skipping the first 4 bytes from that table in order to start to store values. I guess essentially skipping the first checksum value for the DLL. Okay, we can see that happen. And again, it never hurts if you're not sure or you just want a little extra confidence. Let's restart our debug session. Make sure my breakpoint is set. Looks like it is. So we'll go back and step, let's see, one more time. There we go. There's our test EAX. Okay, so now we moved into EDI. EDI is, E3540C. And if we go back to where this was first called, you have 540C, right? The image base is different because we got an different image base in our debugger, but those last few bytes line up, right? And so I'm comfortable with that, saying that, okay, that is in fact the first 4 bytes, and now it's being incremented. Of course, we can see that in EDI. Okay, so we can see this in IDA, just to kind of, again, keep ourselves in sync a little bit. Sometimes, the jumping around, I know if you're trying to follow along, can get a little disorienting. But here we have the move into EDI, the add to EDI4, and then there's a load string dword, and then a compare. So this is going to load into EAX what was in ESI. And if we go back to where the last move into ESI was, towards the beginning of this function, it is the precomputed checksum values. Now, keep in mind that after this load, we incremented. So now we're pointing to, and what EAX will contain is the second checksum value. So really the first API. That's being compared with, and this might have not been in hex right away. Oops, sorry about that. The pseudocode shows it in base 10, so we can just synchronize this in hexadecimal. But then there is the hex value CCCCCCCC. So of course it's looking for the end of. If it finds that those, that the current checksum value is equal to that, then it's going to break. It's done iterating. It's found all of the APIs that it needs. If not, and that's where this branch will take us to the end of the function. And you can rename these two, end of func. That's always helpful. Otherwise, we're going to go down this path, right? And so this is going to then this is now going to take that precomputed value that's in EAX. You see, we have our expected XOR of EAX with this hard-coded value. That's pushed onto the stack as our desired checksum. And now there's a call to direct API resolution, right? And so we don't really need to analyze that because we already have. And because we renamed it, when we encountered it again, I didn't have to remember what sub_405 AEC was. We had a good name for it. That directly resolves the API. And this is where things start to get a little different here. And that instead of just storing that in that global array, that new import table, it's moving the resolved API, the function pointer, into EBX, right? So let's take a look at where EBX is used. Okay, so EBX is used down in, these are ultimately in our case statements. Okay, so you can see that, kind of jumping between the different case statements, you can see in the pseudocode view. So we know that it's going to be utilized there. So we just want to keep track of that momentarily. Now we have a push 10 hex, a push 0, and then a push the argument, which was our new heap, and a call to allocate heap. And so if you look up the call to allocate heap, you'll see that this is the heap to allocate memory on. This is the size of the heap, so 10 hex or 16 bytes. Now, this is going to return in EAX a pointer to that newly allocated memory. And so right now, what we want to watch or trace is what is EAX used for. And you'll see that EAX is used not only in this comparison right after the call, but now again, as we get into these basic blocks, it's going to be used again. Okay, so to help with that, here is in the pseudocode view, our V8 is going to be our new heap memory. And you'll see that after that, we do have this comparison. So this value is moved into ECX, XORed with 10035 FFFF. And then there's a comparison of EAX plus 10 hex. So EAX is the base of this new region of memory, plus 10 hex then would be the beginning, after that allocation, and it's comparing it with what's in ECX. If it equals, that is, if the result of the compare will subtract the two operands, if it's equal, then that means it's not going to enter this branch. That's a little bit different here when we look at it in the decompiler view, because it's going to present that logic, I think, a little more straightforward way, in that it's saying, okay, if the value is not equal to, and let's see if we convert that to hexadecimal, you'll see it's actually AB, 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 AB. If it's not equal to that, enter into this branch, which is this basic block. Now, the significance of this is that you will have certain heap protections that can be enabled, particularly during debugging. And this is part of the heap tail checking, in which it will add, the operating system will add, the memory manager will add this sequence of bytes, AB, 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 as padding after this region of memory was allocated. And so essentially what this is saying is that if it finds this sequence of bytes, then perhaps it's under a debugger and it doesn't call stow SD. It just moves on to this location, right? If it doesn't detect that AB, 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 then we go here. And the stow SD, right, that's going to take what's in EAX. What's in EAX was the newly allocated memory, and it's going to store it in EDI. And if we go back a little bit here, we need to find where EDI was last used. Well, EDI, right, that's going to be essentially our new import table. And so what is happening now is it's not storing the function pointer directly. It's allocating a new chunk of memory. It's storing the pointer to that new chunk of memory there. These are what's going to be called then throughout the rest of this binary. And the rest of this logic here is going to be to move into memory the necessary bytes to call the actual function. So it's that trampoline, or it's the sort of even more indirect way of calling the function. So let's now take a look at what's happening here in this newly allocated region of memory. Okay, so this block, this is EAX. EAX is that pointer to that new chunk of memory. It's dereferenced, and the byte B8 is moved into that location. EAX is then moved into EDX. Right? And so again, this EDX now is going to point to that newly allocated region of memory. We next have a call to sub40110C. And you'll notice here in the pseudocode view, if we highlight that, that's called multiple times here as we get into both this if statement. There's an if and an else branch here. There's the else branch, and then there's case statements. Okay, let's go back up here. What is this function? Well, we could take some time and look at it. It's not terribly complex, although, again, this is one of those that I just generally don't want to have to commit the mental energy to go through it. What it feels like to me when looking at it is you're seeing the pushing of two constant values, push 0 and push 4. And if you look at other invocations of this function, you'll see 1 and 9, 1 and 9, 1 and 9, and let's scroll down. Okay, so 1 and 9 for all the rest of those. This feels like probably that it's generating a random number between a minimum and a maximum, right? And so one way that I could test that theory, kind of similar to what we did with loading of the DLL, is just to set a breakpoint here, step through it a few times, see the result, and if it falls in that pattern, I think based off of the results and the context that we're seeing here, then it makes sense that that's all it's doing, is that it's likely generating or helping to generate a random number. We can go back then to our debugger and set a breakpoint E1 5E06. Okay, you can see there the breakpoint hit, and let's just step through this. Okay, EAX is 0, EAX is 0, EAX is 3, EAX is 0, EAX is 3, it's 2, it's 1, it's 0. Okay, I don't want to go too much further because eventually I'm going to enter out of this region and get into the ransoming. But it would appear just from that simple execution and seeing those results that likely that's all that it's doing. So I'm going to give this a name like maybe generate random number. I say maybe because I didn't actually look at the logic. So I'm not 100% confident because I didn't analyze it, but I'm fairly confident, and I'm not going to go back and look at it unless later on my analysis really demands or dictates that I need to. Okay, so that returns a random number between 0 and 4, and then we have some branching logic here. If it's 0, we go the else branch, in which case this is called again, and maybe a generate random number that just needed update. And the pattern is very similar, as you can see in all of these. If it's If it generated a value that is non-zero, then we're going to enter the if portion, and then we're going to switch on that value. Right? So we could call this, random num, just to help keep track. So then we switch on that, and we have case 1, 2, 3, and 4. And again, that would make sense because we don't need a case 0 because case 0 is handled on the else branch. Case 1, 2, 3, and 4 then would be the remaining cases. So if we generate a number between 0 and 4, that would be 5 potential values inclusive, 0, 1, 2, 3, and 4. So that, again, that kind of lines up, the context lines up. Don't have to spend a lot of time analyzing that function. When we enter the cases then, what happens? Well, in order to answer that, we just need to trace a few more of these registers. And again, this is a situation here where I find the disassembly to be just a tad easier. We go back up to this basic block here, and we have the first byte moved into that region of memory. That was an EAX. EAX was then moved into EDX. And so if we just pick this first case statement, this one here, you'll see that EDX plus 1, EDX plus 5, EDX plus 7, EDX plus 8, right? So EDX represents this new region of memory. This generates another random number. That value is moved into ECX, and then we have a rotate right EBX CL times. Now, what is EBX? Well, if we scroll back up just a little ways here, EBX is our function pointer, right? That was returned right here after the call to our direct API resolution. So CL is a random number that was generated between 1 and 9, and that is then used in order to rotate the function pointer that many times. So it's essentially obfuscating the function pointer. So we're no longer seeing the 4-byte value for wherever that function lives in virtual memory. It's being obfuscated. It's being rotated. That gets moved into EDX plus 1. And then from there, that's a 4-byte value. Now at that new allocation of memory at an offset plus 5, we have this bytes C0, C1. Then we have EDX plus 7. We have the byte CL, right? And CL is the random number that was generated. And then finally, we have EDX plus 8, which is the last 2 bytes. So this might be easier to look at if we follow this in a debugger. So let's take a look at right here, right? So this is apparently the first path that we're going to go down. We have now moved into ECX, the random number that we generated. In this case, that was moved into from EAX. Okay, so we can see those 2 registers, both are 8. EBX contains the function pointer, right? And you can see that that is very clearly stir copy. So now after that rotate, EBX is moved into EDX plus 1. Well, with EDX, we can actually follow this. Let's go to the memory map and do region view. Now we go back to the CPU, we do EDX, we can follow that in the dump, and there is our first byte, B8, and now we're going to move EDX plus 1 EBX. So these next 4 bytes are going to be this shifted value. There it is. Okay, now this just continues. Offset of 5, we're going to move 2 more bytes. Now we got an offset of 7, we're going to move the random value that was generated. There's the 8, and the last 2 bytes will be FFE0, and that's it. And so what this looks like, we can actually follow this in the disassembly, and you'll see there's the logic. So it's moving into EAX, FCA0. So that was that shifted value. That's our original function pointer that's shifted. Now it's rotated the same amount of bytes that it was, that it used that random number to determine how many, and then it jumps to that function pointer. And so that's what these little trampolines are. So for every API that it's resolving, it's not just simply resolving the function pointer for that API, but it's allocating a little chunk of memory. It's further obfuscating the function pointer by creating this little snippet of code. And then during execution, it deobfuscates the function pointer, and then jumps to that address. And if you continue to analyze, you'll see that this just kind of varies the logic in which it is obfuscating those pointers. And we can tell now by the overall flow of this function that it's doing it in a somewhat random manner, because we have random numbers being generated, ifs, and these switches in order to determine the logic here to essentially, and you're going to see that it's primarily to obfuscate that function pointer. And then that's it. Eventually we get to the end of the function and it just returns. And so it's now updated that, and go back to where this is called. It's updated all of these D words with pointers to those new allocations of memory that do the deobfuscation and jump to the function. So let's actually take a look at one of those. Let's rename this first. So let's see, what would we call it? Be a good name for this. Dynamic API with trampolines. Yeah, it sounds good. And you'll see that we're going to continue in the same function here, but now that all the APIs are resolved, that leaves these couple of functions here. And in particular, sub40B444, if we navigate into this, there is a call, right? There's a call to this D word. We can navigate there. You'll see not populated because, of course, this is all static. But we can set a breakpoint, and let's do that. So B465. And let's remove this breakpoint. And let's remove that breakpoint. There we go. All right, so there's our call, B465. Let's step into the call, and there's this little chunk of memory now. There's the the move instruction, the rotate, the XOR, and then this jump, right? So that's what this particular little trampoline was computed, or the path it took in order to create the logic here. Maybe a little different than the one that we just analyzed, because the one we just analyzed didn't do the XOR, just did the rotate. But we stepped through this. As you can see here, we're now ready to jump to EAX, and EAX contains the deobfuscated pointer. And this is going to be to ZW set information thread. Okay, so this gets us into the anti-analysis. I'm going to save that for another video, actually probably the next video, because that makes sense in sequences we're going through this. But to recap, now we understand really the entirety of how the Lockbit decided to implement their runtime linking, their API resolution, and why it wasn't as straightforward as most of the other implementations I see. Two major things, or two, I guess, somewhat significant things. That is the XORing of those checksums, and then these trampolines that have been created in order to jump to those locations. And then the fact that it varies the logic within those trampolines, as you can see here. So you have everything you need if you wanted to go through line by line. All of this is doing. Next steps for this, as you'll see, it'll get really tedious to try to manually look at what each one of these APIs resolves into. We do have, for example, now in the debugger, all of the resolve function pointers, but oftentimes I'm doing a lot of my work in something like IDA. And yes, you could use IDA's debugger to help with this as well, and resolve function imports, but likely at this point you're starting to think, or I'm starting to think of maybe doing some sort of an IDA Python plugin. That'll have to wait for another day, though, because I don't have one created. I do believe there is some good work out there of other authors that have created those plugins. So definitely do a search if you're interested. Remember, this came from Black Matter, that's the theory anyway. Certainly looks like there's a lot of code similarities. So there may be some IDA Python plugins from the Black Matter, and that you could easily adopt. But the focus here was on getting into the technical details and doing the in the weeds analysis. So hopefully we've accomplished that. The next video then we'll look at the anti-analysis, and I think that'll put this the series to an end, because that's all the further I looked at this ransomware.